Hey everyone, and welcome to today's Explainer. We're doing something really cool today. We're tracing two parallel architectures at the exact same time. On one side, we've got the physical evolution of computer memory, and on the other, the fascinating linguistic tools that technical writers actually use to build our understanding of it. So, we're dissecting both the hardware of the past and of mechanics of the English language that define it.
Let's kick things off with a pretty foundational premise. What's the most important function of a computer? Well, its fundamental capability isn't just processing speed, it's storing information long enough to actually process it. The stakes here are all about volatility versus retention. Because think about it, without memory, a computer is literally just a useless collection of wires. That core function drives everything we're going to look at today. Okay, here's our roadmap. 1. The function of memory. 2. Defining the core era. 3. The semiconductor revolution. 4. The bubble memory evolution. And 5. The language of computing. Let's dive in. Section 1. The function of memory, building the blueprint. Right, so before we can truly grasp the tech itself, we've got to understand how authors construct complex technical ideas. When writers introduce a totally unfamiliar concept, they don't just throw a bunch of random words at you. They use a super strict three-part model to completely avoid confusion. It goes like this. First, you have the term, in this case, a core. Next, you place it into a group. It is a ferret ring. And finally, you give it distinguishing characteristics. It is capable of being either magnetized or demagnetized. Term, group, characteristics. It's this highly efficient, logical formula that makes absorbing brand new tech specs incredibly clear.
Moving on to Section 2, defining the core era.
You know, authors actually guide us through history using really explicit time sequence markers. Just like they use formulas for definitions, they use specific phrases to map out a timeline for us. So for our first era, the text uses the marker throughout the 1950s, 1960s, and up to the mid-1970s. That specific phrase tells us exactly when core memory completely dominated the market, grounding all these technical facts into a firm, chronological reality. So, what exactly was core memory? Well, physically, the memory of early computers was made up of these massive grids of fine vertical and horizontal wires. And at every single intersection where these wires crossed, there was one of those tiny ferrite rings, a core. Every single intersection had its own unique address. By passing an electrical current through the wires, a core was either magnetized or demagnetized. That state represented a binary digit, a 0 or a 1. And the capacity? Around 80,000 bits. To put that into perspective, that's roughly 10 kilobytes, which is literally a fraction of a single low-res image on your phone today. But back then, that physical footprint was absolutely massive. Now, here is where the language is absolutely key. A vital characteristic of core memory is described using very specific vocabulary. The word retaining acts as a synonym for keeping. Core memory was highly prized for its capability of retaining information during a power failure. And this wasn't just some nice-to-have convenience. We're talking about massive financial stakes and operational survival for early mainframes. If you pulled the plug on a 1960s machine, your data didn't just vanish into thin air. It physically kept its magnetic state. And that right there is exactly why the text heavily anchors on that word, retaining. Section 3. The Semiconductor Revolution. Okay, let's dive into this next era. Our authors transition us using the exact time marker in the 1970s. This was a further development that completely revolutionized the computing field. And once again, we see our trusty definitional blueprint at work. What allows this massive revolution to happen? Silicon. The text defines the term silicon by placing it in the group of a non-metallic element and giving it the characteristics with semiconductor characteristics. By etching thousands of integrated circuits onto a tiny piece of the silicon, the chip was officially born. Now, the really crucial point here is how this compares to what came before it. When we stack core memory right up against the semiconductor chip, we see a massive leap forward. Semiconductors allow computers to have a memory capacity of millions of bits, making them smaller, way faster, and much cheaper. But there is one major problem, a massive trade-off. Unlike our old friend core memory, when power is removed from semiconductor memory, the information is entirely lost. It just cannot retain its state without electricity. To fully grasp the impact of this era, the source text pushes us to understand antonyms, words with opposite meanings. The antonym for increased is reduced. And because of the semiconductor chip, the physical size of the components containing circuitry was drastically reduced. Mainframes shrank, leading directly to the invention and introduction of both mini-computers and microcomputers. The literal language of reduction paved the way for the personal computers we all use today. Section 4. The bubble memory evolution. The writers signaled this shift into the late 1970s not with a specific date, but with an additive transition phrase. Another development. And bubble memory is a truly fascinating technological leap. How's it actually made? Well, it's this incredibly precise fluid manufacturing process. First, a thin film of metallic alloys is laid over the memory board, which is then magnetized. This magnetization creates these extremely tiny magnetic bubbles. We're talking about 0.1 micrometers in diameter here, microscopic. The presence or absence of just one of these microscopic bubbles represents one bit of information. And the advantages of this leap? Absolutely incredible. Because of how they're constructed, magnetic bubble memories could store information at a much greater density than earlier tech, making them highly suitable for those brand new microcomputers. They're not expensive, they consume very little power, they are incredibly small in size, and they're highly reliable. They effectively solved so many of the major trade-off issues we saw in the jump from core to semiconductor memory. Section 5. The language of computing. All right, we've looked at the history, now let's zoom out and synthesize how all of these technical facts are elegantly woven together. Here is the grand data synthesis, the content review matrix from our source material. This is exactly how focused learners organize complexity. You have the 1950s core memory, large in size, made of wire grids and ferrite rings, holding a capacity of 80,000 bits. Next to it, the early 1970s chip, tiny in size, made of integrated circuits on silicon, holding millions of bits. And finally, the late 1970s bubble memory, extremely tiny, composed of a thin film over metallic alloys, boasting even greater density. The whole chaos of technological progress is beautifully tamed through structured comparison. But getting to that clear comparison requires the author to actively construct meaning. Our grasp of complex computer logic isn't just about understanding the raw hardware, it's about following the linguistic breadcrumbs. Writers shape our understanding using synonyms, like swapping progress for advances when talking about miniaturized circuitry. They rely heavily on contextual reference pronouns. For instance, when a text says a computer stores information long enough to process it, that tiny word "it" successfully bridges the action right back to the data. And they use additive words like moreover to seamlessly stack new capabilities on top of old ones. The language itself is the true architecture of our understanding. Which leaves us with a pretty profound question to think about. We rely on strict formulas, time markers, and precise pronouns to explain the leap from bulky wire grids all the way down to microscopic bubbles. But as computing technology continues to shrink to the quantum and microscopic levels, will our language evolve fast enough? Will we even have the words to accurately explain the memory technologies of tomorrow? Thank you so much for joining me on this explainer. Keep asking questions, and I'll see you next time.